All right. Well, thank you for joining us. You are the person now in the world who I'm most likely to say, "Oh, I wish I'd written that," when I see one of your posts go by on LinkedIn. So I thought it would be a wonderful opportunity to have you come and tell us what you've been learning about Spatial SQL and the kinds of cool things you do with Spatial SQL.
Yeah, absolutely. Well, yeah, thank you for having me. It's exciting to be here. It's kind of a weird full circle moment because you're one of the people I kind of learned a lot from and asked a lot of probably bothersome questions over the years. But yeah, I mean, it's I'm happy to be here.
All right. So take over the screen share.
Sure. Just get the and here we go.
You are online and I can see it. So I'll get out of your way. Thank you, everyone. Matt Forrest.
Great. Yeah, thank you. And once again, thanks for having me. For those of you who don't know, my name is Matt Forrest. I work at Carto. Been over there for about 8 years now. And if you're not familiar, Carto is a platform that works with spatially enabled databases, including PostGIS and data warehouses and different tools. And more of our work has kind of drifted into looking at what's called the modern data stack, and which is a broader concept within the bigger data space. And how does that apply to geospatial, and where does spatial SQL and PostGIS fit into all of this? And this is sort of what our agenda will be today. We'll be looking at sort of what is the promise of the modern data stack. When we talk about it, what does that mean? And how does that sort of translate into a geospatial data stack? My argument and the way I've been using things is PostGIS is still very central to this entire process. And a lot of these new technologies really flow through and work well with PostGIS being sort of your central geospatial data store. So everything can kind of live through that, including all these different tools, working with simplified vector data from GeoParquet, scaling up and using PostGIS plus DuckDB, which is a really cool tool I've been using a lot lately, especially for really large files or remote files, and then automating some data processing with DBT, or data build tool, which is sort of like an orchestration pipeline that you can manage data transformations and set different rules, and doing that all with SQL. So that actually connects into DuckDB and Postgres as well. So you can actually ingest and manage data, append tables, overwrite, do all these different things as you get new data in, which is really great. The next is looking at why H3 and PostGIS work so well together. That's one of the last things we'll cover, and kind of why I really like H3 within PostGIS, probably the most out of any tool I used H3 with. And then finally is actually PostGIS and how I think it's set the standard for rasters and databases. More of our work has started to look at including analyzed raster data, whether that be a lot on the climate side or climate change and things like that. But I think it's just a really nice experience having it in a database, and PostGIS just has the largest amount of tools around that. And a lot of the raster work we're doing is kind of modeled similarly off of what PostGIS has done with the tiling and different components and functions within it. So a little bit about the modern data stack, if you haven't heard this term before. It really sort of originated with a few different things, but there's a few core pieces. First are your sort of your data warehouses or databases, starting with BigQuery, Snowflake, and Redshift. These kind of new, big data tools and, sort of distributed queries and, lots of computing power. You have some of your BI tools that have, become popular, outside of of course, Tableau. You have Looker and, mode analytics and more that are coming through. You also have your sort of your ELT, your transformation layer. These are commercial tools. Fivetran is one. There's another open source one that I like called Airbyte. But the whole concept is basically taking source data and loading it into your data source as effectively as possible, and then doing the transformation within the database, which is where tools like DBT come into play. Actually, once the data is loaded in, you take that and then you transform that data once it's landed in your database. And then the last bit is you have some different layers on sort of your data governance and things like that. And those are some of the new tools. So this is kind of a short evolution of what that's looked like. Why is this taking place? Is that there's definitely growth in demand for the OLAP database, or online analytical processing database, that people are using for sort of the larger data sets. And we're not talking spatial yet, but just the things like, event logs, or sales or transactions or anything like that that can be really long and many rows. Being able to do that quite effectively, and distributed computing has a core component in that, and updating that with regular releases. A key piece here that I think is really important is that SQL is sort of the lingua franca as you look at all these different tools working together. More and more, everything is kind of coming back to SQL in one way or another. DBT writes SQL. Your transformation tools are, pulling into SQL. You're analyzing your queries in SQL. You're piping that into BI dashboards in SQL. So everything kind of comes back to that in one way or another. And then you have this full ecosystem of tools that, as you'll see, is starting to come up together. But what really, I think, what sums it up is that the world of traditional big data used to be really complicated. You had Hadoop, and you had to spin up all these different things to make it work, and it was all these interconnected pieces were just it was a big problem for lots of organizations to actually work and create this infrastructure. But the modern data stack promises a simpler approach. There's like one tool for one specific thing. They all work nicely together. So it's kind of similar to what AWS tried to start with, is instead of having everything on your on-prem machine and you had to install and update there, you could use your storage for one thing with S3, you could use your compute with EC2, and you could use your database with their RDS, which is sort of like their core primitives in their data stack. So this is kind of a similar concept. If you look at this chart here, this kind of describes at a very high level, this is your sort of traditional data stack where you have a manual intensive on-prem process. You're dumping your structured data in, there's a sort of change resistant ETL layer. And here it's more like you have multiple data sources coming from HTTP data. You have maybe, there's popular graph data, or things like coming in from Spark or a database, and that kind of lives within this sort of lake house, right? And there's all these little tools that are interconnected, and then that all goes out to applications or reports or analytics tools. So when you hear these terms like lake house or modern data stack, this is sort of how you can think of that. And this is sort of this person's argument about like what's the next data stack or the data first stack beyond that. So looking at kind of almost in a way back to this and adding some different pieces onto it, but that you can read that article if you want. What this looks like, and you'll see charts like this. This is a chart from MotherDuck that kind of talks about, here's your data sources that come in, here's how you manage the ingestion, some of those ELT tools I mentioned, like Fivetran and Airbyte. You have reverse ETL to take the data you've processed and push it back to data storage, whether that be like S3 or blob storage or any of these other tools. Your transformation layer, there's some orchestration layers down here, and then basically the outputs like business intelligence or data science or anything like an application layer like that. Similar concept here, you see the same thing. Core is like the data sources, data integration, and like the EL extract load layer, do the transformation and data storage, all these different pieces that work together. So that's kind of the core of like what all of this is together. But what is the modern geospatial data stack? And this is my first attempt I've kind of started to put together about what this looks like. I think, you'll notice some different pieces here, but obviously from the data sources side, you have your cloud native raster data here, different data portals, whether those be government or online sources, things like AWS Open Data, your storage that lives on S3 or Google Cloud Storage, and things like GeoParquet. So you have all these data sources, managing ingestion. I look at kind of Airbyte as sort of potential. There's some different pieces there that you can use. It's a good tool, and there is an open source version, so you can orchestrate that and many other data layers really nicely. But I think still GDAL kind of remains one of the core, being what if you need to transform and bring that into a storage layer, it's really efficient to do that. Or if you need an orchestration layer, Airflow does that nicely as well. From a storage side, the new cloud data warehouses are certainly prevalent. I think there's adding some spatial capabilities, but like I said, I still think PostGIS be kind of due to its interconnectivity to so many different tools, how it connects in, and I'll show that in the slide in a minute, and how it can actually fit with everything here. Remains very essential to the process, especially with the amount of spatial functionality. The data warehouses certainly have a core set of spatial functions, but nowhere near the volume and the vastness and things like that. And then, of course, on your transformation layer, we'll be looking at H3, represented by this icon here, and DBT a little bit too. But GDAL tends to pop up, I think, in all of these as well, just to integrate and do some of these different pieces here. And then this is sort of your output layer. This is a very simple chart. There's many more things you could do with this, but that's a mapping sort of output, maybe a data science output, or maybe some application layers and things like that. So the pieces we'll be looking at today are here. These are all kind of the components about what you can do with these different pieces, how you can work with sort of your PostGIS, how it integrates with these different data layers and things like that. And what that sort of looks like, and what we'll talk about, is how PostGIS connects with all of these. We're going to be going through a sample use case about how you can use all these different components together and how they connect really nicely, even into your AWS open data, raster data, or remote files for GeoParquet or anything like that. Ingesting data and connecting it with GDAL and bringing that in as sort of a layer to push data back and forth really efficiently. Using DuckDB and actually using the foreign data wrapper for DuckDB within PostGIS is something that I think is really great. They launched their spatial extension, which adds a lot of spatial functionality. So there's certain things it does really, really well at scale, and you can read remote files and all these good things. But being able to take some of that as a transformation piece and then bring that into PostGIS to do maybe larger complex spatial joins or different things there are really essential. On the output side, we're not going to look at too much of this today, but there's certainly core connections with QGIS, as I'm sure many of you know, GeoPandas, and tools like LeafMap, which is, I think, fast becoming a really very cool toolkit from the Jupyter Notebook kind of side of Geospatial. And then on the last bit from the transformation using DBT, in this case, we'll be going from DBT to DuckDB to PostGIS, but there's obviously you can do direct connections into PostGIS should you want to and orchestrate it that way. And then finally, looking at H3 cells. So this kind of sums up my argument to say why I think PostGIS still remains an essential player, and just like you said, it's so connected into all these different pieces so nicely. And that's kind of my argument today, is like that's what we'll hopefully come back to, and I'll hopefully prove that point to everyone today. So we'll talk about the case we'll go through is a little bit about weather and analyzing weather data that kind of lives across different places in the web. I grew up in Minnesota, so this is a Halloween blizzard that I grew up with. I think I was about 3 years old, but I remember trick-or-treating, the snow was above my head. So that's one. And then in 2011, we had another, I think it was like a 28-inch or 30-inch snowstorm where the Metrodome actually collapsed under the weight of the snow. So, these were the storms I was used to growing up, certainly large amounts of snow. But when I moved to New York, we've had a few storms like Sandy, and there was some flash floods in 2021. But this was just this past fall. We had these torrential rain remnants of a hurricane, and this is just in the middle of Manhattan, a street where people are walking through. It's just overwhelming amounts of water and rain, and this is a real image from a subway with water just streaming down it. So these flash flood type events have gotten a lot more frequent. I think there's even smaller ones that we can point to, but it's one of those phenomena that I think is somewhat hard to track, knowing what's there and what's where and why you want to figure out where those storms take place. Generally they're categorized as storms with lots of rain coming at a specific time, but it's actually hard to pick out, okay, what is a flash flood and where have they happened? Are they increasing? Are they changing? And we do have data for that. It's just maybe not as necessarily accessible as we might want it to be, which is where our tools come in today to actually put all that together. So this is data made available by NOAA. It's the Historical Storms Database. It is a FTP with multiple gzipped CSV files that there's one for every year going, there's a few breaks in it, but it goes from 1950 forward. So there's a few areas where the years break, and I think they maybe have a couple years in there, but there's 3 sort of tables, as it were. If you think there's like a storms details layer, there's information about fatalities, and then there's information about the storm events. And it has a very in-depth like event narrative data that actually tells you what's taking place. You can see where the storm started and the storm ended. There's a bunch of other data that you can pull from this, but it just isn't necessarily like the most accessible thing in the world to pull all these files. And of course, they update all the time. These, if you see these dates here, this is 2022, 0425. As you get down further, these dates will change, and the more up-to-date data will have a more frequent timestamp on it. So it changes quite a bit, which also makes it difficult to keep up to date with what's in there. So this is what we'll be doing. Will be kind of our simplified architecture for today, using some cloud optimized geotiffs that are surfaced through a spatiotemporal asset catalog or stack via AWS Open Data. We'll be pulling in some simple DEM data just to say, okay, in certain areas we want to understand what's the elevation, raster statistics in that area. With our CSV data, we'll actually be processing some of that first in DuckDB just as a bulk upload, and then we'll set up a DBT workflow to process that data as new events and details become available. So it can actually process that, pull it in, and then actually surface it in PostGIS. So all this data will push in kind of through this workflow, and then using the DuckDB foreign data wrapper, you can actually analyze and use that in PostGIS alongside your other data that you're using. From a GeoParquet side, we won't touch too much on that, but just to know that DuckDB has the ability to push out GeoParquet files, so you can save them, have maybe some more consistency on the outputs of those files that you've analyzed, and using them there. And that's kind of the core. And then we'll touch a little bit on using H3 within PostGIS as kind of a final layer to help scale analysis a little bit more within there. So the first job is we're actually going to load in what's known as the FEMA National Flood hazard layer. That's a layer that basically, if you think of what's your flood zone for your home, at least in the US, that's what you're measured off for insurance. So we're going to load that in, and the only way to get that is from a Esri JSON. But fortunately, GDAL will help us here to take that Esri map server layer and bring that right into PostGIS. These are pretty complex. It's a large, detailed polygons with lots of different data behind them, but this makes it pretty easy to grab that and pull that in and actually use it to make it useful. So it's nice just to be able to grab that server layer, pull it in, and just have that ready to go. So that's what we'll be analyzing against, is this national flood hazard layer. We'll be trying to look in that and see for the different flood zones, how many storms that we are categorizing as flash floods exist in each one, and then what's the relative elevation over each of those zones. So that's kind of our base geometry, if you think of it that way. And just being able to use complex polygons, I still think PostGIS is the best at this, to analyze them, use them, do spatial joins, do all these different pieces at scale. It's really performant, and all the work that's gone into functions like st intersects just make it really valuable to continue to use PostGIS in this way. The next is DuckDB to run a one-time import of that gzipped CSV data. Now, what I really like about DuckDB is its ability to just kind of run anywhere. If you're not familiar with it, it's a columnar and vector OLAP, and there's no dependencies, and really no dependencies. There's nothing you have to install except DuckDB. You can run it just on your machine through the command line, or you can use its Python extension. You don't need to have a database. It runs very much like if you're familiar with SQLite, it's sort of like that for analytics, and it's really great for large amounts of data. And once again, you can read data from a file system or a remote file system. In this case, that's what we're doing with the CSV files. It has a spatial extension, so that was released, I think, in March. And it was released and then actually made a core part as a core extension of DuckDB. So when you install it, you actually install with the spatial extensions. There's no extra work you have to do there apart from loading it in when you open your database. And it's really great. I think it can do quite a few things. There's some cool things they're doing with a new geometry type called 2G geometries that works well with kind of that vectorized database. Not vectorized, I should say, but the columnar and vector OLAP that works really well there. So there's some things that adds some speed performance in there. But for the most part, you can read multiple different remote files if you have that. It connects in with GDAL and can read those remote files and does everything that way. So there's some really cool pieces there for that really large scale stuff, or some of these kind of annoying tasks of reading remote files, which is what we did here. So if you see at the top, this is the database that we'll eventually be connecting to and reading with. with our foreign data wrapper to PostGIS. But basically what we want to do here is, create a table in our database. You just create a database file like you might in SQLite. And then you read these multiple CSV files. You can join as many as you want. These are just the files from 2019 to present. And you just pass them into this array, read the CSV, you pass in an auto detect for the schema, and it will automatically pick up that it's a gzip file. How do we actually categorize what is a flash flood? Is we're actually going to use the free text search index, and then create different tables to actually search across the event narrative. So what this does is it kind of works like you might think of like a Google search or sort of like a text searching. So we can look for the words flash flood, like we see here, and we'll select all the columns and we'll get a score to see how basically how much they think it's close to a flash flood. And this is what we get back. So you might not even mention the words flash or flood, but you can kind of see a stream gauge on Cherry Creek reported a 3.61 foot rise. So even though those words aren't in there, it contextually can pick up that this seems like a flash flood. About 8.85 inches of heavy rain fell in about 30 minutes. Street flooding was reported, overflowing drainages. So these are all things that sound like flash flooding, right? And this is, like I said, it's kind of one of those things that's hard to pick up. We know where like big floods are going to go with those storm layers, but it's hard to pick up what's going to happen with flash floods. And I think this is a really just interesting way to grab this really rich text data and just apply some sort of numeric metric to it. So these are the numeric score matches as it goes to each of these. And you can kind of see that they get less and less as you go down. So things like hail here, or like, large amounts of hail in a short period of time are starting to show up. So these get much lower scores from that side. So now we actually connect PostGIS with DuckDB via the foreign data wrapper. And there's this great article that shows exactly how to do that. You can actually, do this from remote files. You can add in a database file from DuckDB to do this, but effectively what you're doing is just like any other foreign data wrapper. You have to install that, connect that to your PG config, and then you can actually set up and connect DuckDB and run DuckDB queries as a foreign table in PostGIS. Which I think is really great, is that we can do this processing over here in DuckDB, or if we have like, let's say, some sort of crazy join to like really long data. If you think of like city bike data where there's maybe a couple, 100 bike share locations, but millions and millions of trips, you can let DuckDB handle that like really complex join, and it's very, very quick to do that. And then you can actually do some of the more spatial analysis in PostGIS and kind of use both tools for their best advantage, but everything's kind of flowing through PostGIS. You're running DuckDB queries in pg-admin, which I think is really incredible here to do these two pieces together. So this is when I say like it becomes more of a central component. This is where you start to see all the dots connecting here and how this all works together. So of course we have new storms data that's coming in. So there's data that we are loading in that's processing. So anytime that data updates, we can create a simple process to basically handle this and turn it in and process it into DuckDB. So we'll go basically use DuckDB into DBT, and then that we can then insert that into that remote table that we're reading in. So once we create that remote table, it's going to be basically updated, ready for us to use in PostGIS when we're ready to go. So what that looks like, there's basically a few steps to install your DBT project here. You're going to basically create what's known as a profile. So you give it your DuckDB and your path. And then you give it your URL, and you get to put these kind of like parameters in here, and here's the parameter name for the table here with that date stamp. And then all you're doing here is basically this is the first step where you can have and string multiple steps together. But if you're able to see that, I should go back to that SQL query. I should have stopped it on there a little longer. But what happens is you're actually able to take once the data is loaded in, you can run that query as you see there. You don't actually have to load it in because you're reading that remote file just as you see here. And then all you're doing is just doing some simple casting to create the geometries. And then the next step, you can create the FTS function to actually run and then recategorize that data. And then from there, you create a third step that basically pushes and appends your table. And now you have your new data in. It actually looks and sees if there's duplicates or anything like that. So it handles that whole process for you. So basically you go in, you type in the command line, dbt run, it runs, and then you're done. So you can do that as many times as you want. And then once again, once it's in that appended table, you're just right back in PostGIS doing what you need to do. I should also mention that there's a Postgres connector for DBT as well. So if you want to go straight to Postgres there, you can certainly do that and run it that way. And now when I think one of the cooler things, like I said, I've worked more with rasters lately, and I think just having them in database and using them through SQL is like it just makes life for me a lot easier because I'm so used to writing in SQL. I've worked mostly with vector data my whole life, so it's kind of been one of those things like if I need to pull it in, maybe I'll open in QGIS and clip, and then maybe vectorize and then go from there, or try and like do some stats there and re-upload that data. And now I don't have to. All those functions exist in a database, which is amazing. And not only that, we're going to load a DEM. It's not a file. It's actually from a cloud optimized GeoTIFF that exists in a spatiotemporal asset catalog from AWS Open Data. So I don't really have to do anything to get this data. I just have to find it correctly and hook that in. So this is the data. If you go to the registry of open data, you'll find they have lots of raster data sets that are available, but it's the Copernicus 30-meter DEM. They have a 90-meter version as well. But then it actually, as you see here, has this nice little stack endpoint for us to use. If you open that up, you'll get a big XML document, which is, you probably wouldn't be able to read it, but there is this really great stack viewer that has been developed, and it's an open source project. You can download it or just use the online version. And they have a lot of projects that are already loaded up. So they actually have the full AWS catalog here that's accessible via a stack endpoint. And what you can do is you can see all of the different cog files that exist. They're basically, I think, segmented by different lat long coordinates and things like that. So you can figure out which ones you need, and then basically just grab that cog endpoint. If you click on the data here, you get the URL for your S3 bucket. It's a public data set, so you don't have to do any sort of like extra authentication there. But if you do, you can do that as well in PostGIS. So you're actually just kind of importing and connecting to this remote file. You can read that out. This is the S3 endpoint for this that specific DAM you want to grab. If you want to grab multiples, you can obviously do that as well. And then you're basically going to pull that in, and then you can basically have and pass in variables once you're running raster to PGSQL, and then you can actually get your AWS keys, and then in PostGIS you can set those keys as well. So it can just it's basically just reading a remote file, which is incredible. It's a remote raster file that you're reading and querying within SQL. It's just, I think that's so cool. So what do we do now is we have all this data. We're going to basically aggregate our flash flood scores. So we get, as you see here, we're just going to get the sum of the scores. We're using just baseline score as a metric. I'm sure there's more advanced ways you could do this for what a flash flood might be. And we're going to join that to each of the different flood layers to try and understand, okay, if there's an event near there, what would that look like? And it's just doing a simple intersection right now, but you could, look at that within a certain, distance or whatever that might be as well. And then join those together to get that value back. And then next is actually looking at the spatial statistics. So you have these great raster functions to do summary stats. So we can get your total number of pixels. You can get the minimum elevation, maximum elevation, average elevation from that DEM, and understand, okay, what does that look like from an elevation perspective in that single area for a pretty granular raster file that you are just accessing from AWS. You're just using that remotely all within, and this is just my local PostGIS instance I'm running with Docker, which is just running all this for me. So I have all these different pieces running here, but it's all running through and connecting nicely. But don't forget, there's one more thing we mentioned that we were going to talk about, which is H3s. Let's say, this works, at scale for like some maybe smaller areas or things like that. But if you really want to go crazy big or do things like that, the H3 functions are incredible within PostGIS, and what the package I've been using, there's a Docker compose function for Carto that basically has a lot of the packages pre-installed, with PostGIS PG routing, topology, and then some of the H3 functions as well, if you wanted to add those in too. So you can just kind of run that, start that up and run those packages, and then you're basically have all your extensions set and ready to go without a lot of other heavy lifting to do from there. And the great part is, I think, for H3 cells, if you're not familiar, it's like a global discrete gridding system. You can actually join on the string value. And what's really great about it, I think, is that you can actually polyfill polygons really efficiently, like probably the most efficiently I've seen that's out there, because a lot of the cloud data warehouses, we've at Carto built UDFs to do that, but the native functions just aren't existing yet. They're starting to roll them out, but within PostGIS, it's incredibly fast just to fill a polygon, figure out what those H3 cells are. You have the other points that you can map up to that, and then do a string join on like a massive scale of area. And then you can visualize different things like this. This is just a DEM that I turned into elevation. So it's just basically taking the average, or you can do summary stats across each cell here, basically finding the centroid of each pixel and aggregate that. It's a pretty quick query to actually run. But then you get something like this. This is just visualizing Carto to show, okay, here's all this elevation from a random DEM around Denver. So it's super fast to do some awesome stuff like that. So just kind of going back to all the pieces together, it sounds like I know it sounds like we're talking about a lot of different new or technologies or parts of the data stack, but I think they all come in and live really nicely together under PostGIS, and that can be just this central component that you're using to maybe do some kind of crazier work in DuckDB, or joining to a lot of big long CSV data. You can come back and do H3. You can connect to remote rasters and do all of that in this kind of central place. So I hope I kind of proved the argument. I think PostGIS remains a central part of that. And just a quick note, actually releasing a book today with Locate Press. So this is out as of about 20 minutes ago, a whole book on Spatial SQL. There's a code there for everyone here today for 30% off, so you can go and get that. And yeah, that's I hate doing shameless plugs, but I'm excited to have this out in the world and live from there. So that's my presentation. Yeah, thank you.
Wow, well, congratulations on the book. That's a big accomplishment. I guess there's a few other authors in the channel who can testify that writing a book is a lot of work.
Oh, yeah.
But it's a great step. Thank you so much for sharing your experience. I'd love to harangue you with questions, but we got to move on to the next talk. We're at the top of the hour. Thank you again, Matt.
Yeah, thank you.